Hi, in today's lecture I will be discussing about the control strategies of chopper, in which I will discuss about pulse width modulation control, and then the variable frequency control, and the third one, which is the current control strategy of the chopper. And afterwards I will also do discussion on the step down chopper as well as the step up choppers. Okay, so let's begin with the control strategies of chopper. Choppers are basically DC to DC converters, and whenever we have input DC and we want to step up that DC, then we use step up choppers, and when we want to step down it, we can have step down choppers. So, in order to control the uh, DC at the output side of the load, there are different strategies of control which a chopper can adopt. So, the first strategy is the pulse width modulation, and over here you can see the chopper is doing what? It is converting the supply voltage into an average voltage, which is a control voltage. So this is the controlled voltage appearing at the output of the load in a chopper in pulse width modulation control. So in pulse width modulation control, the chopper does what? We have the supply voltage, and in between the supply voltage and the load we have a switch which is turning on and off, and it is by turning on and off it is varying the uh, width of the it is you can say the width is being varied. And once the when we have a supply voltage and we have a load, supply voltage at the left hand side and load at the right hand side, and in between we have a switch, and when we switch it off for a longer duration, then small width pulses will be happening over here, and due to which the average voltage is up to this level. So whenever we turn on more than offing the switch in between the supply voltage and the load, then the width is increased. So when the width is small and the average voltage is medium, and when the width is large, T on is greater than T off, then the V average voltage which is appearing across the load is higher. So in this way, by varying the width of the pulses, by controlling the switch in between the supply and the load, we are varying the T on and T off, and in that way we are varying the output control voltage or the V average output voltage. In this formula you can see V average output voltage is equal to supply voltage multiplied by T on time divided by the summation of this T on plus T off, which is always equal to the duty cycle, which is equal to T on bata total bata T. So, second control strategy is the variable frequency control strategy of the choppers. In this strategy, we are doing what? Is that we are varying the frequency of the pulses, and the width of the pulses is always constant. And over here you can see we have, this is a constant width of the pulse, and this is this one. Here the frequency is small, and when the frequency is small, then we have a low average output voltage, and when we increase the frequency of the pulses from the supply voltage to the load, then the average voltage is increased. So in the a variable frequency control, we have between the supply voltage and the load a switch which is behaving in such a way that it is outputting constant width voltages to the output. But when we use that switch in such a way that it is switching at a fast rate, then it is like sending fast at a faster frequency the constant width pulses at the output side. And so that in that way, when the switch is doing fast switching, the average output voltage is small, and when it is doing the fast switching, then the average output voltage is higher. So in that way, by varying the frequency of the switch in between the supply voltage and the load, we are able to control the average output voltage which is appearing across the load. So then the third strategy of controlling in the choppers is the current control strategy, In this you can see we are over here have a DC voltage, and we have a diode, and we have a resistor, and we have the inductor, we have a switch which is doing on and off. So what happening over here is that what is happening over here, we have two phases. In the first phase we have this switch which is closed, and the supply voltage is appearing across the load in such a way. And when the current is moving in this direction and over here, because it is not moving over here because this diode is reversed biased. And when this switch is off, the inductor behaves as a kind of current source, in which you can see the current is moving in this way through the forward bias diode and through the load in that way. So in this way, if we can see the waveforms, we can see that whenever the switch is in on, it is closed, then the voltage will be appearing across the load at the output side, and whenever this switch is off, there is no voltage which is appearing across the load, and the inductor is behaving as a current source. See, so in both phases you can see that whenever we have the voltage which is appearing across the load, the current is increasing through the uh, load, and whenever the voltage is not the switch is off, the inductor behaves as a current source, and the current is decreasing through the load in such a way. So it will be the current which is will be decreasing and increasing in such a way. And there are two levels of current, one is the I1 and other is the I2, and the difference is the delta I, which can also be said as a ripple of the current. So there are different advantages of this current control strategy of the chopper. uh, you can read those over here. The first one is that it is not requiring an extra filter, because it is we are doing what we are just controlling the current, and this the change in current can be controlled by varying the parameters of the load at the right hand side. You can see by varying these parameters of the load, we can control the ripple of the current, and in that way we have in very much power electronic circuits where we require the current to vary. So it has very much applications in those complicated circuits in which we are to vary the current on the load side, and we can use this circuit over there by which we can vary the current on the load side. And there are multiple applications of it. We can use it in the DC motor by for varying its speed. We can use it in the switch mode power supplies as well. And this is a chart which is giving a description of the difference between all these control strategies of the chopper, and you can see it from here. Now I will discuss about the step down and step up choppers. This is the circuit of a step down chopper, in which you can see we have over here the DC voltage supply, we have a load which is attached over here, we have a switch over here, we have a diode over here, we have an inductor over here. Whenever this switch is closed, the current is coming from this direction from the supply, and it is passing through the inductor, through the load, and then dissipating over here. And whenever the switch is off, this inductor behaves as a kind of you can say current source, and the current will be moving from here and in this direction over here. So let's see the waveforms. If we see at the output side over here, what is the voltage during the on closed, when the switch is closed, what is the voltage on the side of the load? You can see that the supply voltage will be appearing on the load during the on time, and when the switch is open, there is no voltage appearing across the load. And similarly, if we see the current on the load side, we can see when the supply voltage is appearing across the load, the current is kind of increasing, and when there is the inductor which is behaving as a current source and no supply voltage appearing across the load, the current is decreasing, and it is behaving in this pattern continuously. And this is you can say whenever we can if we are able to calculate the average output voltage on the load side, then we have this formula in which we have the supply voltage, and we have the duty cycle which is T on by T on plus T off, and we can say this parameter as alpha, and we always know that this parameter is less than 1 because t is greater than t on, and when t on is divided by t, then it is a parameter which is smaller than 1 always, and when that smaller than 1 parameter is being multiplied with the supply voltage, the output voltage is always smaller than the Vs. So this is uh, what a step down chopper does. It step downs the supply voltage into an average voltage into a smaller voltage, and in those circuit it is being utilized where we want to step down the DC voltage from a higher level to a lower level. Now we can see the step up chopper in which we have the supply voltage, the inductor, the diode, the load. We have a switch over here, and during the T on, when this switch is closed, we have the current which is coming from here, supply to the inductor, passing through over here and like this. And whenever this switch is off, the current is coming from here, passing through the inductor, through the diode, through the load, and then dissipating over here. So in this circuit, the current is behaving in this way. Whenever we have the switch is being closed, the current is a kind of you can say at the output side there is no current. This is the supply current. Whenever we have the T on during the T on time, when this switch is closed, then there is no current which is appearing across the load. But when we have during the T off time, when this switch is off, the current is appearing across the load, and it is in that way appearing across the load, and this cycle continues. And whenever we want to calculate the energy during the T on and T off time, then this is the formula for the energy, which is P on into T on for the on state energy calculation. And we can see over here P on is equal to Vi, and during the T on time the V is equal to Vs, and I is the average of these two current levels, which is I1 into I2, I1 plus I2 divided by 2 during the T on time. And during the T off time, the energy is equal to P off multiplied by T off, and P off is having Vi formula, where V is Vs minus V naught, and during the T of time we have this Vs and then this is V naught, so the overall voltage will be Vs minus V naught. So Vs minus V naught into I, the same relation as for the previous expression, and we have the T of time. And here if we are assuming it like that, when E1 is equal to E2, if we assume that both these are equal to each other, then we can do the calculations and we are able to calculate the V naught, which is Vs into 1 minus alpha. So alpha is always smaller than 1, and 1 minus smaller than 1 is always smaller than 1, and when the smaller than 1 is being divided by 1 is divided by that smaller than 1 entity, then it will be a greater than 1 entity over here, which is when multiplied by the Vs voltage is always greater than uh, uh, the Vs voltage itself. So it is a kind of step up chopper which is doing what? It is stepping up the supply voltage to a higher level voltage, which is V naught. Thank you very much.